Morning, everyone. Welcome. Hi, everyone. Today we're going to talk about enthalpy cycles, and especially we're going to be looking at these middle three things I put in red. We're going to be looking at Hess's law, bond enthalpies, and enthalpy cycles. I'm an IB chemistry teacher, Meg Hennessy, working in Houston, Texas, in the USA, and I'm excited to do this with you. If you have any questions, feel free to throw them in the chat. And when I ask multiple choice questions or anything, feel free to answer them so I can keep a pulse on how I'm doing and if everyone's following along. I can't wait to get started. I wanted to make sure to share my notes with you. And so here's a quick little QR code that you can use to view the notes. And if that's not working for you, I'm sharing a Google link in the chat as well. So I'm going to give you a second to get that sorted. And we're going to start calculating some enthalpy. It'd be great if you had a calculator or a data booklet. All of the values that we're going to use are in the presentation, but just to get ready for that exam that's coming so fast, it might be great to have it to figure out where some of these numbers are kept. Ooh. Okay, onward. So we often think about enthalpy in terms of the change in energy between two states. And so I have reactants A going to reactants B. And you can see that that's an exothermic reaction. B is lower in energy than A. And so we could write down that the delta H, the change in enthalpy for this reaction, is -10. What do you think would happen if I made that arrow go the other way? Well, of course, if I go from the products back to the reactants, we would expect that we're going to have exactly the opposite enthalpy. And so the delta H for the reverse process is just the negative of the delta H of the forward process. And if we take these two things together, we get Hess's law. Hess's law says that if we go around a complete circle, the total change in enthalpy is going to be 0. And so today we're just going to be using Hess's law to solve a lot of different problems. Yeah, I'll send the link again for the slides. I'll send it a few times. I know you can't see the chat until you've joined us. So there you go. No worries. Please let me know what you need. We're a small enough group that if you have questions, I will do my best to answer them. And so I wanted to make that kind of simple example maybe a little bit bigger. And so I put in a new thing, C. And so you can see I'm kind of interested in figuring out how to go from A to C. And I claim there are two ways to solve this problem, and hopefully they'll both make sense to you. One way we can solve this problem is we can try to use exactly Hess's law that we saw a minute ago, which says if we can make this into a circle, we know the sum of the enthalpy changes has to be equal to 0. And so if I want to go from A to C, this is my question mark. If I wanted to close this circle down, I can see that all of this is linked together, but then this one is backwards. I'd really like to flip this reaction. And so I could write down that 0, the total enthalpy change for going around an entire circle, is equal to the enthalpy change of going from A to C plus the enthalpy change of going from C to B minus the enthalpy change of going from A to B. And I could plug in my values. I know C to B is -18. That's this value here. I know A to B is -10. And I could solve for A to C. And hopefully, if I didn't drop that minus sign, it's a little early in the morning for me, we could solve that as 8. But I think that's not how most of us would set this problem up. I think most of us would set this problem up by noticing some algebraic relationships between the equations. I think most of us would say, gosh, you're interested in going from A to C. I can't go directly from A to C. That's not the data that I was given in this problem. Instead, what I'm going to do is I'm going to go from A to B and then from B to C. So I'm going to make this a two-step problem. Well, I know how to go from A to B. That value's directly in the data. It takes -10 kilojoules per mole. And to go from B to C, I have to reverse that second equation. So it takes +18 or a -18. And hopefully, if I add those two things together, I get the very same 8 kilojoules per mole. What I'm trying to convince you of is that Hess's law says go around a circle, the change in delta H is 0. But the way that you and I apply it more often is to say, well, I'm interested in this reaction. How can I reconfigure other reactions so that I can combine them algebraically to get the one that I want? I think it's all going to make sense in a second. If you're not feeling good, feel free to throw a note in the chat and I can re-go over something. I'm here for you. Let's see how it's going. So I took this question from the RV website just to see, can we add delta H's in a way to take two equations and sum them to a third equation? And again, if you're interested, please feel free to throw that answer in the chat so I can see if I'm giving you enough time to think. All right, so I'm seeing some agreement that the answer should be option D here. And we could try to do this by just going through the possibilities and seeing if they're true. In answer choice A, I'm interested in solving for the delta H for step 2 here. And instead of going directly from A to C, as I want, I'm going to have to go indirectly. I'm going to have to go from A to B and then from B to C. A to B is the forward process 1, and B to C is the reverse process 3. And so answer choice A is not correct. I can do this for each of the options, but I'm just going to fast forward because I saw the right answer was D to make sure that makes sense. And I'm going to look at D. D says that delta H1, so that's this one, going from A to B, is going to be equal to going from A to C and then going from C to B. So I don't have to flip either of those arrows. I'm just going to add the two steps together, and I'm going to write down that delta H1 is in fact equal to delta H2 going from A to C and then going from C to B. So instead of going directly from A to B, we went through step C. We kept in mind the direction of the arrows that we were given, made sure they were all pointing the right way, and D was the correct answer. Good job. If anyone's still looking for the notes, here's another opportunity to grab them. And we're going to make the problems look a little bit more chemical in nature, a little less theoretical. There you go. So I was teaching my students a little about fermentation and making biofuels. And so I just came across these equations and thought it would be fun to see if we could use them to figure out the delta H for that top reaction, for taking carbon dioxide and liquid water and turning them into glucose and oxygen. Now, a lot of you recognize that that process is photosynthesis. And so maybe we can just take a second and say, if my delta H isn't positive, I've done something wrong. It's a little less clear where A and B and all that stuff is, but I know how to rearrange my equations to make them algebraically similar to my target equation, to that top equation whose delta H I don't know. And what I mean by that is that glucose appears in the product side here. And so I want glucose to be a product of my reaction. And if I want glucose to be a product of my reaction, I'm going to look at this first reaction and say to myself, well, it's backwards. And so I've got to flip it around. And when I flip it around, what's going to happen is I'm going to multiply delta H by -1. So whenever you reverse a reaction, you reverse the sign of delta H. And what does that look like? I think I did this in a whole bunch of steps. Well, I now have glucose on the right-hand side and the correct side of my equation. And you can see that I changed the sign of delta H by multiplying it by -1. So what's next? What else isn't quite right about this? Well, I notice I have this ethanol here, and there's no ethanol in my target equation, so I would like it to go away. How can I make it go away? Well, if it right now appears on the reactant side, I can make sure that it appears in the same amount on the product side. So what I'm thinking about doing, because I have ethanol right here, is multiplying this equation by 2 and flipping it. So multiplying it by 2 is going to ensure that the coefficient is the same, and then putting it on the product side is going to ensure that the ethanol will cancel out. So let me show you what that looks like. There you go. We multiplied by 2. You can see that here. And we flipped it. We took that delta H and we multiplied by 2 and negated it. And we should be able to add these two equations together. And if the stars align, we should be done with this problem. So there you go. The 2 ethanols here cancel with the 2 ethanols here. I have 2 CO2s plus 2 times 2 more is 4. 2 and 4 is 6. So I have 6 total CO2s. I have 2 times 3 is 6 waters. I have my glucose, and I have 2 times 3 is 6 oxygens. So when I add these two equations together, I get the overall equation I was going for. And the delta H for my overall equation is just the sum of the delta H's of each of those steps. So we're using Hess's law. So someone asked, why do we multiply by -1? And or exchange the sign? Those two ideas are the same. If you flip a reaction, you're going to take the opposite sign. And mathematically, I think that's the same thing as multiplying by -1. So if you say exchange the sign at school, that's exactly the same idea. I'm really glad that this reaction has a big positive delta H, because again, I recognized that this was photosynthesis. And so I knew that I needed sunlight for the reaction to take place. If you want to see it look a little bit more like a cycle, you can say, well, I can't get directly from carbon dioxide and water to glucose and oxygen because I wasn't given that data. But I was given some other data. I was given some data about how to ferment the sugar to make ethanol and CO2. And I was given some information in the second equation about how to combust that ethanol. But when we combust something, we only combust a mole of it. So I multiplied that reaction by 2. I have 2 moles of ethanol, 2 moles of ethanol. And so if I wanted to go from left to right in this picture, from the reactants to the products, using the data that I was actually given, I'm going to have to flip this first reaction after multiplying it by 2 and flip this second reaction. And that's exactly what we did algebraically. So that's why this unit is called enthalpy cycles, because even if you think you're solving the problem a little bit differently, you're using Hess's law, so you're using an enthalpy cycle. I worked through this a little bit more slowly if you have those notes open, just so that you could follow along if you ever looked at this presentation again. So I showed that first step was fermentation. I blacked out the oxygen because it wasn't involved in that step. I didn't need it until later. So energetically, it wouldn't change any values. That appears to be the same slide. Let's not look too hard, everyone. In the second step, I burned the ethanol. And again, I had to burn 2 moles of it. So you see I had that coefficient of 2, and I multiplied delta H by 2. And then I recognized that I had to flip these signs around to get the answer that I wanted. So this is the same thing I worked through with my pen. Just if you come back and want to see this, I wanted you to see this step by step. So this is using Hess's law or adding equations to figure out the delta H of a reaction we're interested in. So I worked through one example. I wondered if you guys could work through one on your own. So I'm going to give you like 30 seconds just to think about how you would start it. I know that's not enough time to work the whole thing, but I have 3 equations whose enthalpy change I know, and I'm looking for the delta H for that target reaction in red. And I just want you to think about how you might approach the problem. What is the first step that you're going to take to solve this problem? When I solve these algebraically, my goal is to make sure that the unique things, unique means they only appear in one of these equations. The unique things like ammonia or like NO appear on the right side of the equation with the right coefficient. And so when I look at this problem, my first step is to pick out the things that only appear once. Some of you are saying, why didn't she circle the water? It's just because I can't read fast enough. The water is also unique. Why didn't I circle the oxygen? Because oxygen does appear in 2 equations. And so I don't have a lot of control about how that coefficient is going to work out independently. So I'm just going to hope that that works. And I promise that it will. So if I wanted my 3 equations to look like my target equation, I could go through and tell you that the first one, what I want to do is I want to multiply it by 2. I want to multiply it by 2 because I want the coefficient of NO to be 4. It's on the right side of the reaction, so I'm not going to flip it. I'm going to leave it alone. For the second one, ammonia has the wrong coefficient also. The coefficient here is 2, but in my target equation, it's 4. So I'm going to multiply it by 2, but it's also on the wrong side of the equation. So I'm going to flip it and multiply by 2. And that means I've got to take the enthalpy change and multiply it by -2. So I change that sign when I flip it, and I use the 2 to get the coefficients right. Finally, water has a coefficient of 2 in the given equation. It has a coefficient of 6 in the target equation. It is on the right side, the product side. And so I'm going to multiply it by 3 to get that coefficient to be correct. And I'm going to multiply delta H by 3. Now, if I trust myself, I'm done with the problem. I just have to add these 3 values together. And so it depends how I'm doing on time, what my next step is. So if I'm someone who's a bit of a slower worker, I'm probably going to trust myself and I'll go back and I'll check my work later. But if I'm a super fast worker, maybe what I'm going to do right now is just check it. And what I mean by check it is super fast, try to write down what each of these equations would be if I went ahead and did those manipulations. If I multiplied the first one by 2, if I multiplied the second one by 2 and flipped it, and if I multiplied the third one by 3. When I make my first math mistake, feel free to let me know in the chat. Doing these problems by myself, I'm pretty accurate, but sometimes I get a little nervous when I'm doing something like this. So just feel free to let me know if I make a mistake. I'm not embarrassed. I'm just doing my best. What I'm going to do when I add these equations together is I'm going to cancel out anything that appears on both sides of the yield zero. So 2N2 cancel with 2N2. I feel like something else could cancel. 6H2 cancels with 6H2. And I'm going to sum. I'm going to have 4 NH3s and 5 O2s come together to make 4 NOs and 6 H2Os. Oh my gosh, we did it right. And so the delta H is going to be the sum of these 3 values. And I'm plugging that in my calculator, hoping I don't make a silly. And I got 1644.6 kilojoules per mole. One more time, I like to do a little gut check. This reaction looks a lot like combustion. I'm mixing something with oxygen. I'm oxidizing it. I'm making liquid water. I am relieved that my answer is negative. If I got a positive answer, I would go back and just double check that I hadn't done something wrong. So again, my slides try to go through this a little bit step by step, so you have a souvenir of how we did this. Actually, they don't. My slides just show you my answer in perfect penmanship because I don't always write super neatly, but it shows what was canceled and how we multiplied. And I hope that you got my thinking through our work together. So that's Hess's law, just adding equations together. So the first example of enthalpy cycles. If you came in a little later, here's the last link to the notes I think I have in here. Again, if you have any questions, feel free to put them in the chat. And we're going to move on to something else after we practice a multiple choice question. So I just went into the question bank and I found a cute multiple choice question about this. Don't be sorry. Let me double check my math. Yep, I got that too. That's awful. I put some paper 1 and paper 2 questions throughout here. If you go on the website, there are plenty of questions that you can check out in that question bank, Lakshmi. Eleanor, like, yeah, you're right. I did plug it in my calculator wrong. I did it twice wrong, so I'm really consistent, but I apologize. So I'll fix that in the notes in a minute, but you're right. Thanks for doing it. If anyone solved this multiple choice question, feel free to throw an answer in. Here you have to know how to write the enthalpy of formation of carbon monoxide. That's our next unit. Enthalpy of formation is taking elements in their standard state to make what it is you have in mind. So of course, it's going to be something along the lines of carbon and oxygen reacting together to make carbon monoxide. And overall, I'm seeing what many of you did was you flipped this second reaction. You added them together and you got choice D. Excellent. So we're going to leave choice A alone. We're going to keep it going forward because it has the right reactant, carbon. And we're going to flip the second equation because it has CO on the wrong side. So the best answer here is D. Okay, now we're going to move on to something a little different. We're going to talk about bond dissociation enthalpies. And bond dissociation enthalpies, it's a definition that comes up a lot on the exams. And the two things that you have to know beyond the fact that it's about breaking bonds is that you can only do this in the gas phase and that the numbers in the table are averages over representative compounds. And so often that's worth 2 marks, knowing the gas phase and knowing the average. So a question could be, why is this technique for solving a problem less accurate than using enthalpies of combustion or enthalpies of formation? Your answer would be because it represents an average. It's not for these unique compounds. Or why can't you use bond dissociation enthalpy to solve this problem? Well, because this problem includes solids and bond dissociation enthalpies are only accurate in the gas phase. The formula that we use here is that the delta H of a reaction is going to be equal to the sum of all of the bond dissociation enthalpies of the bonds that are broken minus the sum of all of the bond dissociation enthalpies of all of the bonds that are formed. That's a lot of words to say, so I typically just write broken minus formed. And to show you how that looks, for a given reaction like this one, we're going to combust some ethene. What we've got to do to solve the problem is figure out what bonds are present. And to figure out what bonds are present, we're going to have to draw some Lewis structures. And so you're going to go ahead and write down the Lewis structure for ethene. Hopefully you're noticing that everything here is in the gas phase, so this is a great technique. Your Lewis structures don't have to be perfect if you don't put in lone pairs. When it asks you for a Lewis structure, of course, on the exam, you wouldn't get credit. But here, we're really interested in just the bonds that are being made and broken, so you can be a little bit lazy, but I won't be. I'll just admit that I don't need it. Okay, so I drew some Lewis structures. So now I have an idea of what bonds are going to be broken. Those are going to be the bonds in the reactants. And what bonds are going to be formed. Those are going to be the bonds in the products. And so I can go ahead and I can make a table and say what I've got to break is a carbon-carbon double bond, 4 carbon-hydrogen single bonds. And get this, there's a coefficient here, so I can't forget that. 3 oxygen-oxygen double bonds. And over here, let me again write down those coefficients so I don't make a silly. In carbon dioxide, there are 2 carbon-oxygen double bonds, but there are 2 molecules of carbon dioxide. So when I think about what bonds I formed, I'm going to take 2 times 2 is 4 carbon-oxygen double bonds. And same for water. Each water molecule contains 2 OHs, and I have 2 water molecules. So overall, I think I have 4 OH bonds. If I go to section 11 of the data booklet, I can then figure out how much energy this is going to cost. So I have a little cartoon of section 11 coming up in the next slide. So there you go. There are my Lewis structures. And section 11, it looks like this. So we're going to say what's bonded to what. So for example, we had a carbon-carbon double bond, and that's located below the big table. All of the multiple bonds are below the big table. But we had an oxygen-hydrogen single bond, and you would find that right here in the table, and oxygen and hydrogen, 463. And so I put those values all together. Ooh. And we broke 1 carbon-carbon double bond, 4 carbon-hydrogen single bonds, 3 oxygen-oxygen double bonds. And I found the total energy associated with breaking all of the bonds was that number, 3,764. Similarly, I took the energy of forming the 4 CO double bonds and the 4 OH single bonds, added those all up. I got 5,068. I took the bonds broken minus the bonds formed. I added that together, and I got negative 1304. And I was really pleased that it was a negative number because, one more time, this is very close to combustion. I'm taking a hydrocarbon, I'm adding oxygen, I'm making carbon dioxide and gaseous water. I'm not making liquid water because I'm using bond dissociation enthalpy. Everything has to be in the gas phase. Nevertheless, I expected this delta H to be negative, and I feel pretty good that it is. So that's how we could use bond dissociation enthalpies to figure out the enthalpy change of a chemical reaction. To go back to this idea of cycles, maybe to help you remember that it's bonds broken minus bonds formed, I'm going to take a second to show you what you did. So those reactants, I drew them all out. And the products, I drew them all out. So this time I incorporated the stoichiometric coefficient, the fact that there were 3 oxygens and 2 CO2s, and I showed them all to you. And what I can look up in the table is how much energy it takes to break the bonds. So if I broke every bond here, I would be left with a whole bunch of gas phase atoms. And if I broke every bond in the products, if I broke the 4 C double bond O and the 4 OHs, I would end up with a whole bunch of gas phase atoms. So these are the values that I get for free from table 11 in my data booklet. And the question is, how can I use them to solve for the enthalpy change of this reaction? Well, because it can see the cycle now, what I recognize is that I can't go directly from the reactants to the products. I have to go through this intermediate of the atoms. This one's going great. It's going the right direction. But this one is backwards. I want to flip this reaction. I actually want to form the bonds in the products. And so if I wanted to know the delta H for this reaction, or for any reaction, it's going to be the sum of all of the bonds that are broken. Again, that's what's going to do this first line, getting me to those atoms, minus the sum of all of the things that are formed. That's me flipping this second reaction around to make the atoms back into products. So this formula, broken minus formed, is just saying I'm applying Hess's law using data from section 11 or table 11 in my data booklet. Again, if you have any questions, please let me know. That's the same thing in a prettier version. You can see our final answer is up here and that we negated this step. We made sure that we made bonds in that second step instead of breaking them as the data gives us. And so I wondered if we could use this to think about two isomers of C3H4, cyclopropene and propyne. Can we use bond dissociation enthalpies to determine which one is more stable? When we talk about stability, frequently you might think about an energy profile picture. And in that energy profile picture, we could have the reactants and the products. And maybe a picture that looks like this, where this is the reaction coordinate. And some of you are like, ooh, kinetics. I see an activation energy there. But this reaction, where the products are lower in energy than the reactants, is exothermic. Energy had to be released to the surroundings because the products don't have it anymore. Another way of describing this reaction is saying that the products are more stable than the reactants. When something is stable, it is of lower energy. You're at the bottom of a hill. If you're a marble, when it's at the top of the hill, it has a bunch of potential energy, but when it falls to the bottom, it's stable. It's no longer going to do anything. It's just going to sit at the bottom of that hill forever. And so the same with these chemicals. These products are very stable. So I was thinking when I solved this problem and I saw the word stable, that the real question here might be, is this reaction endothermic or exothermic? So if it was endothermic, it would look like this. We would have to take energy in from the surroundings and give it to the chemical system to make the products higher in energy or less stable than the reactants. And so if I could do this problem, what that would mean is the sign of the enthalpy change would give me the answer to the question. I'm finally done annotating my picture. And I'm going to think about these two isomers. So I have cyclopropene and propyne. I'm going to convert one to the other. And I'm going to see if that reaction is endothermic or exothermic. So what would that look like? I have cyclopropene. And I'm thinking about converting it into propyne. And my question is the enthalpy change for this reaction positive or negative? So I'm trying to figure out which one of these is more stable by solving for the delta H. And the way I'm going to solve for the delta H, because these are both in the gas phase, is by figuring out if the bonds broken or the bonds formed have a higher enthalpy. Or I'm going to sum up the bonds broken. And here that's going to be a carbon-carbon double bond, 2 carbon-carbon single bonds, and 4 carbon-hydrogen single bonds. I have section 11 open, and I have 614 for the bond enthalpy of breaking the carbon-carbon double bond, 2 346s for the bond enthalpy of breaking the carbon-carbon single bond, and 4 14s for breaking the CH bonds. And over here in the products, I'm thinking about forming 1 CC, 1 C triple bond C, and 4 CHs. The CC has a bond enthalpy of 346. The C triple bond C has a bond enthalpy of 839. And the 4 CHs each have a bond enthalpy of 414. So the delta H for this reaction is going to be the sum of all of the broken minus the formed. And so maybe I should do the calculation again. Oh my goodness, that is so not it. I got 2962 minus 2841. And I got then 121 kilojoules per mole. So this reaction is endothermic. So since this reaction is endothermic, that would mean to me that propyne is less stable, it's higher in energy, and cyclopropene is more stable, it's lower in energy. And so which of these isomers is more stable was our question. And our answer is cyclopropene is more stable. It's because we were able to calculate the delta H of this reaction. We used the sum of the bonds broken minus the sum of the bonds formed. We found that was endothermic. We knew then that the products were less stable than the reactants, or that propyne was less stable than cyclopropene. Let me know if you have any questions on that. I have one for you to try, a multiple choice. Feel free to throw your answers in to chat. Thank you. Trying to answer some questions in here. I just don't know if it's practical. Okay, thanks for those of you who answered this question. You guys suggested that the answer was A. Again, you're going to have to go ahead and think about what the multiple choice options here do is they write out the values without having you solve the problem, but we're still going to have to draw some Lewis structures to make sure that we're catching all of the different bonds involved. Of course, the formula here is bonds broken minus bonds formed. So I'm looking for something that has 4 CHs. So that's all of these. plus 2 OO double bonds, so C and D appear to be incorrect, minus 2 COs, minus 4 OHs. So definitely I agree with you that the answer has to be A. Well done. Yes, Jesse, you can say that. Oh my God. Okay. Ooh. Aside from that, there is a Google Sheet. If you'd like to give me some feedback on how this is going, feel free to use it. This link will come up a few times, but we're going to move on to enthalpy of formation. So for enthalpies of formation, it's defined as the amount of energy required to make 1 mole of a compound from its elements in their standard state. So this is that one time when you're balancing chemical equations and you actually have to use fractions. Since there's only 1 oxygen on the left, I am required to use half a mole of O2 because the coefficient for the methanol in this example must be 1. So you must use fractions. You need to make sure that the coefficient in front of your product is 1. We're going to use all of the elements in their standard state. So that means carbon's a solid, it's graphite. That means that hydrogen, oxygen, nitrogen, fluorine, whatever are diatomic gases. Also remember that the enthalpy of formation of any element in its standard state is 0 because it doesn't cost any energy to make what you're starting with. So if I give you a bunch of graphite and say, how much energy does it cost to make graphite? You're going to say none. I've already got it. So those won't appear in table 12 of your data booklet because you're supposed to know that the values are 0. The big formula here is that the delta H of the reaction will be the sum of all of the enthalpies of formation of the products minus all of the enthalpy of formation of the reactants. Those N's that I put in mean that you do have to account for the stoichiometric coefficients. So that's what that means. If you don't like my summation notation, you can just say to yourself, it's products minus reactants. I stole a few values from section 12, and we use section 12 for calculating delta H's from delta H of formation, for calculating delta G's, and for calculating delta S's if you're in HL from the absolute entropies of things. But in each of these cases, whenever you're using section 12, you're going to use the formula products minus reactants. And so I had in mind this esterification reaction. I chose it largely because you can see that there are liquids. So we don't have to worry about things being in the gas phase. That's not part of the definition of this technique. And so if I wanted to calculate the delta H of this reaction, it's just going to be equal to the delta H of formation of the products. So I'm going to go and I'm going to find methyl ethanoate. It's minus 432. And I'm going to add to that the enthalpy of formation of liquid water. Be careful that you do use the right one. Both vapor water and liquid water are in the table. And it's a really common mistake to just use the wrong one. And then I'm going to subtract all of the enthalpies of formation of the reactants. And so I'm going to put in methanol, and I'm going to put in ethanoic acid. And that's the whole problem. It's just, again, the sum of the enthalpies of formation of the products minus those of the reactants, everything multiplied by its coefficient. That's it. Oh, miracle. To give you a sense of how to use this in a cycle, the cycle is about formation. So again, it's about taking elements in their standard state and using them to build stuff. So if you're looking in that table, what you actually had was the enthalpy of taking carbon and oxygen and hydrogen and putting them together to form the methanol and the ethanoic acid, or putting together carbon and oxygen and hydrogen and combining them to form the ester and water. What you were interested in was, of course, this reaction, the direct esterification reaction. And so maybe you can see that I can't go directly from the left to the right. What I'm going to do is I'm going to flip this guy and take the second one in the right direction. So it's going to be the enthalpy of formation of the products minus the enthalpy of formation of the reactants. So putting it into a cycle helps me remember the sign. I know that the delta H when I'm using enthalpies of formation is always products minus reactants. And here I can see why. It's because this intermediate that I'm using down here, the elements, are what I'm using as a starting material for these things. And so I need this reaction to run backwards because I want to go from the reactants to the elements, not the other way around. I broke that into the two formations here so that the numbers are on the picture. And finally, I'm going to flip those two reactions around in order to get the delta H that we want. So there we go. It's the same 5.2 kilojoules. Again, just a little bit of a souvenir if you want to look at this again. So enthalpies of formation, products minus reactants. And to see how that went, we're going to try to do one together. We're going to say, given that the enthalpy of combustion of sucrose is that big number, minus 5,640 kilojoules per mole, determine the enthalpy of formation of sucrose. Wow. All right. I know that the formula I use whenever I'm looking at section 12 data, whenever I'm looking at enthalpies of formation, is going to be that the delta H of a reaction is equal to the sum of the delta H's of formation of all of the products minus the delta H's of formation of all of the reactants. And so if I were to burn sucrose, I'm going to make carbon dioxide and liquid water. If I want to balance that equation, I'm going to notice that I need 12 carbon dioxides to balance the 12 carbons. I'm going to need 11 waters to balance the 22 hydrogens. And then I'm going to need 12 O2s so that the sum of the oxygens on both sides is the same. I think it's 35. And I'm told that the delta H of this reaction is minus 5,640. But I also know that the delta H of the overall reaction has to be the sum of the enthalpies of formation of the products minus the reactants. And so I could write down that minus 5,640 is equal to the delta H of formation of CO2. But I can't forget that coefficient. There are 12 of them. And it's going to be the delta H of formation of liquid water. But again, I don't want to forget that coefficient. There are 11 of them. Minus the delta H of formation of the sugar. And 12 times the delta H of formation of oxygen. So I'm going to pull out my data booklet and I'm going to look up these values. And I'm going to say minus 5,640 is equal to 12 times minus 393.5 plus 11 times minus 285.8 minus, this is the value I'm actually looking for, the delta H of formation of sucrose. And the delta H of formation of oxygen is just 0. It's an element in its standard state. So I did the algebra earlier today, and let's just hope that I didn't mess it up. I got that the delta H of formation is minus 2222.5 kilojoules per mole. And with such a cool number, I can't believe it's not right. So we used the formula for delta H's of formation. Anytime you're directed to section 12 in the data booklet, that's the formula you're going to use, products minus reactants. But here the question was asked in a slightly different way. We were given the delta H of the reaction, and we had to solve for one of the delta H's of formation. The IB is quite generous in telling us which section of the data booklet to go to. And so as soon as you go to this table, I want you to think this is the formula I've got to use. Again, any questions, throw them in the chat. I've been doing my best to answer them when they come up. So there's me trying to do it earlier today. I'm going to move on to the third thing, and that's the enthalpy of combustion. So there are 3 tables in the data booklet that refer to enthalpy. The first was bond dissociation enthalpy. That was section 11. The second is enthalpies of formation. That's section 12. And this enthalpy of combustion is section 13. This is where you take 1 mole of usually an organic molecule, you react it with oxygen, and you make carbon dioxide and liquid water. And what's interesting here is that my slide is really big there. Maybe you can see it better now. What's interesting here is that the formula has actually flipped around. It's really important to notice that here the reactants minus the products is the formula. So for formation, products minus reactants. For combustion, reactants minus products. That's a big deal. I'm going to try to show you with cycles why it makes sense, and I'm going to give you a little mnemonic to remember if you think this is something that you could use some support with. Just as a fun fact, when you look at this table, all of the delta H's of combustion will be negative numbers. And this goofy balanced equation, it is the general form for balancing an equation for the things in section 13, but I think it's just a little extra. So let's see if we can use this equation. Let's see if this is hard. And the answer is a little bit. So we're going to try to take some cyclohexane and hydrogenate it to make cyclohexane. And the way we're going to do that is we're going to be told, hey, look at section 13 and figure this out. And whenever we look at section 13, we approach the problem the same way. We say that the delta H of the reaction is going to be equal to the delta H of the reactants, the delta H of combustion of the reactants. So looking in my table, this is just cut from section 13. I'm going to take the delta H of combustion of cyclohexene, C6H10. I am going to add the delta H of combustion of H2, that's minus 286. And I am going to subtract the delta H of combustion of the product, cyclohexane, that's minus 3920. And so again, anytime I'm directed to section 13, I know already how to solve the problem. I know it's a reactants minus products problem because that's how the table works. Hopefully, you're going to agree that the delta H for this reaction is negative 166 kilojoules per mole. So best case scenario, they say, go to section 13 and solve this problem. And you say, of course. I'm going to resend the link for the slides, just in case anyone joined late. I'm going to send them to everybody. Uh-oh, well, you can't. Okay, apparently that's going to be slightly harder than I dreamed. I can't cut and paste because, of course, I'm in Zoom. Okay, everybody, let's take a deep breath. It's probably more for me than for you. And I was going to try to just go back in time and show the link. Sorry if this is annoying. There you go. Those are the questions in the slides. I did not send out any pre-reading questions. I know some of the math folks do. But just in case you've been sitting there like, gosh, I wish I had these slides. There you go. And we're going to be back at enthalpy of combustion in a second. Again, I'm doing my best to answer any questions that come up in the chat. So feel free to throw your questions there if you've got some. And we're going to be back talking about enthalpy of combustion. Okay, we just solved this problem. We said it's products, it's reactants minus products because it's a little bit goofy, but straightforward. And so just to show you why the formula is different, I set it up as a cycle again. Combustion is about adding oxygen to things and making sure that you make carbon dioxide and water. And so combustion is going to be the forward red arrows. So one more time, I'm interested in going from the reactants to the products. If something isn't in the data booklet, it would be given in the problem. My little box on the right-hand side shows the values that you would have access to. I can't get directly from the reactants and the products. I've been told that I have to go to section 13. When I go to section 13, I find these values, but they all refer to burning the stuff. So they all go in the down direction. What I'm going to have to do is I'm, of course, going to have to flip the reaction on the right. I want to uncombust the cyclohexane. Consequently, this reaction, the delta H, is going to be the sum of the delta H of combustion of the reactants, because I left that reaction going in the forward direction, minus the delta H of combustion of all of the products, because that is what I had to flip around this time. And so this picture guarantees that I don't make a mistake in the sign, because it's something I'm prone to do. So if you think of it in terms of cycles, all three of the formulas, broken minus formed, the delta H of the reaction is equal to the sum of the enthalpies of formation of the products minus the reactants, and the delta H of the reaction is equal to the sum of the delta H's of combustions of the reactants minus the products, all make sense. But when I'm in the exam, sometimes making sense isn't enough. And so I do have a little mnemonic that will help you after we've practiced. So could we figure out the enthalpy of formation of phenol using enthalpies of combustion in section 13? So phenol is the formula C6H5OH. And what I'm interested in doing is figuring out the delta H for the formation of phenol using section 13. So I know that overall, I'm meant to be using the formula that the delta H of the reaction is the delta H's of combustion of the reactants minus the delta H's of combustion of the products. So I'm going to write down the equation for the enthalpy of formation of phenol. Remember that the enthalpy of formation is defined as taking elements in their standard state to create 1 mole of my compound. And so phenol has carbon in it. So let's take some carbon graphite. And phenol actually has 6. So let's take 6 moles of carbon graphite and react that with hydrogen. Hydrogen in its standard state is a gas that's diatomic. There are 6 hydrogens here. So I'm going to take 3 moles of H2 gas. And then the last ingredient I'm going to need is oxygen, which is also a diatomic gas. And like I promised you, we're going to have to go ahead and use a fractional coefficient here because I only need a single oxygen. And the reason I need to use that fractional coefficient is because the definition of formation is making 1 mole of your product. So this here is the delta H that we want. And this delta H must be equal to the sum of the delta H's of combustion of my reactants. So my first reactant is carbon, and I have 6 of them. So I'm going to put that coefficient here. And my second reactant is hydrogen. So I'm going to take the delta H of combustion of hydrogen. And I'm not going to forget my coefficient. I'm going to multiply it by 3. And then I'm going to take the delta H of combustion of oxygen. And I'm not going to forget my coefficient. I'm going to multiply it by 1/2. And then I'm going to subtract the delta H of combustion of phenol. So when I look in the data booklet in section 13, some of this data is there for me. The delta H of combustion of carbon is given. The delta H of combustion of carbon is minus 394. The delta H of hydrogen is given. The delta H of combustion of hydrogen is negative 286. But oxygen isn't there. If you have any bright ideas about what oxygen's delta H of formation might be, throw them in the chat. The delta H of combustion of phenol is there. It's minus 3053. Yep, you're right. The delta H of combustion of oxygen is 0. Remember, combustion is taking something and mixing it with oxygen and seeing what reaction will happen. When I mix carbon with oxygen, I make carbon dioxide. When I mix hydrogen with oxygen, I make water. But if I mix oxygen with oxygen, I've just got oxygen. Nothing's going to happen. And so this is something sneaky that has come up in a paper before that you might want to remember, that the delta H of combustion of oxygen is 0. You can't combust oxygen. Anyway, the delta H here is going to be the sum of all of these values with the correct signs. And as long as I haven't made any silly typos, I hope that we all get minus 169 kilojoules per mole. And so we just solved for the delta H of formation of phenol. And we did that using the delta H's of combustion. And we knew where to look in the data booklet because the problem statement almost always tells us. So there's no mystery there. You're not going to be sitting there thinking, where do I look? You're going to be directed to, please use section 13 to solve this problem. And whenever you use section 13, reactants minus products. While delta H's of combustion are always negative and bond dissociation enthalpies are always positive, enthalpies of formation are both positive and negative. And I'm not able to do a great gut check here to know if my answer was meant to be positive or negative. So exothermic means that energy is given off to the surroundings, or that delta H is negative. And endothermic means that energy is absorbed from the surroundings, or delta H is positive. So there's me with the souvenir. And here's my silly mnemonic. I kind of fell in love with ChatGPT's ability to make silly pictures. So I wanted something that would help me remember the formulas. For products minus reactants is formation, and reactants minus products is combustion. And so I have a fox looking for proof in the crepe. Proof, products minus reactants, formation. Crepe, combustion is reactants minus products. I don't know why it made me laugh, but it was just a moment of trying to get a presentation together and it being late at night and me thinking this was funny. So I hope it helps you just keep in mind the direction of those things: products minus reactants for formation, reactants minus products for combustion. That's actually in the data booklet for the new syllabus because it's just such a common thing to get wrong. And so I hope that this will help just one of you keep in mind the signs. If you didn't get a chance to leave feedback before, here's another opportunity for you to see that form. We're going to be moving into some of the higher level content now. So if you have any questions, feel free to ask them. And if you're not interested in learning about Born-Haber cycles, I hope you have a wonderful rest of your day. So the Born-Haber cycle is a step-by-step process that we use to try to calculate things that we can't experimentally do. So the lattice enthalpy is what we usually think about. The lattice enthalpy is the amount of energy it takes to take a solid, crystalline, ionic lattice and blow it apart into gas phase ions. It is always a positive number, and it's always a pretty big number because it takes a lot of energy to break all of those ionic bonds. But I can't really do that. And so we come up with this really convoluted scheme of reactions that we can do and a way to sum them together to get the information that we want. And so my master formula is here in red, and it's correct, but it's a little bit undecipherable. One of the things I wanted to point out to you is where things are located in the data booklet. And so the numbers underneath are where you would find lattice enthalpies in the data booklet. They're in section 18. Where you would find ionization energies in the data booklet, they're in section 8. Where you would find bond dissociation enthalpies, section 11, and where you would find electron affinities, section 8. Both the enthalpy of atomization and the enthalpy of formation of a ionic salt are not in the data booklet. They either are what's being asked in the question or they're in the question statement itself. So a lot of times you're both going to be hunting in the data booklet and reading the problem statement for information here. But I put in a lot of the things that are coming up, just where you would find this, because these problems take time if you haven't practiced knowing where to go to get the information that you need. So even if you're an expert on Hess's law, as no doubt you'll be, just if you can't find the bond dissociation enthalpy because you forget what table it's in, it's just going to take you that little bit of extra time. So there you go. And so the question that I have in mind is, can we figure out the lattice enthalpy of sodium oxide? And as I promised you, the question statement will often give us some information. And this time it's giving me information about the enthalpy of formation and about the enthalpy of atomization of sodium. So the two things that I told you we might need some help with are in the question statement. Not every lattice enthalpy is in section 18 of your data booklet, and sodium oxide is one of those that I think is not there. Now, I'm going to try to show you what's going on pictorially. I hope it helps. Right here, I have the ionic lattice. So you can see that I have the cations and anions arranged together in a repeating 3-dimensional or 2-dimensional, if you're picky, array. And the lattice enthalpy, which again is in section 18, is the amount of energy required to take that lattice and blow it apart into gas phase ions. One more time, this reaction is always super, super endothermic. So that's what this question is asking about. And what our task is going to be is to say, well, we don't know what this is. What kind of a cycle can we put together that will be an alternative pathway from the lattice to the ions? Another piece of information that was in our problem statement was the enthalpy of formation. So let me get that in my picture. The enthalpy of formation is going to be the elements in their standard state making whatever it is you want to make. And in this case, we had the enthalpy of formation of sodium oxide. And so it's going to be the enthalpy associated with taking the elements sodium and oxygen in their standard state and putting them together to make sodium oxide. And that's going to be a pretty negative reaction. So I'm closer, but I still haven't closed this gap. And so we're just going to go step by step and think about what we could do and define the different terms. So one of the things I notice is that the sodiums are still, like this sodium, sorry, the sodium is a metal, and so it's a solid lattice. And so I'm going to have to atomize the sodium. That means break something apart to make 1 mole of gaseous sodium atoms. And so the enthalpy of atomization is going to be the energy associated with making 1 mole of sodium atoms. Now, you might have noticed that we're talking about sodium oxide, which actually contains 2 moles of sodium. And so you can see I have that coefficient 2 here because I'm actually going to need 2 moles of sodium to do my bidding to get this subscript 2 in line. So that's atomization. We usually use atomization for the metal, and it's taking the solid metal and separating it into 1 mole of gas phase atoms. Since we have 2 moles of sodium, because it's Na2O, we're going to be multiplying that value by 2. We're closer to where we want to be, but we're going to have to ionize the sodium. So when we ionize the sodium, we're going to have to use the ionization energy, which we would find in table 8 of the data booklet. So I've taken the sodium, I've removed the little black electrons from them. They're still there. Sodium got smaller because it lost that valence electron in its 3s orbital. It's now Na plus, and that's actually what I have right here. So the sodium is ready to go. We took the sodium metal, we atomized it, we ionized it, sodium's ready. And so the next thing we're going to do is get the oxygen ready. So right now the oxygen is a diatomic molecule. So we're going to have to break apart that diatomic molecule to make oxygen atoms. And when we break apart that oxygen molecule to make oxygen atoms, we're going to go back to the bond dissociation enthalpies. Bond dissociation enthalpies, that is section 11, break 1 mole of the bond. That means they make 2 moles of O atoms. I only need 1 mole of O atoms because my formula here is Na2O. There's only 1 O. And so that's why I have this coefficient of a half. I don't need 2 moles of O atoms. I need 1 mole of O atoms. So I only need to make half a mole of O2s break apart. And consequently, I only need to pay half of the bond dissociation enthalpy. So our oxygen is now atoms. It's not yet O2 minus. That's going to take 2 steps. I'm going to do 2 electron affinities. First, I'm going to make O minus, and then I'm going to make O2 minus. So that is the cycle. Those are the values you know. Those are the tables where you find them. Pictorially, this is what Born-Haber is doing, and it's super complicated. But each step is one that you've practiced before. You became expert in ionization energy and electron affinity when you were learning about periodicity. We've been talking about bond dissociation enthalpies today. We've been talking about enthalpies of formation today. A new vocabulary term would be lattice enthalpies. Again, taking an ionic lattice and breaking it apart into gas phase ions. And atomization, that is making 1 mole of atoms. And so there's my silly formula, keeping in mind the signs that are associated with the arrows. So the 2 black arrows, formation and lattice enthalpy, as given in a problem statement, as given by their definition, go from here to here. And the other steps start at that same element and go all the way around this circle to these gas phase ions. And so it must be true that those 2 paths sum to the same thing. That is to say, the sum of the formation and the lattice enthalpy, F and L, has to be equal to the sum of the atomization, taking the sodium and breaking it into atoms, the ionization, making sodium plus, the bond dissociation enthalpy of oxygen, that is making the oxygen atoms, and then making the oxides, the electron affinity. So those 2 sides must be equal because of Hess's law, because this is an enthalpy cycle. And so while the first equation I think is formally good, the second equation is something that makes a little bit more sense to me. It's certainly easier to write. Maybe this is a more typical way you've seen this, where I have energy increasing in the y direction. At the bottom, I have the lattice. If I take the elements and I combine them to make the lattice, that's the enthalpy of formation. And then you can see atomization, ionization, bond dissociation enthalpy, electron affinities. And that other piece is, of course, the lattice enthalpy, what we are solving for in the problem that we right now are supposed to be doing. So the question I asked you like 5 minutes ago is, what is the lattice enthalpy of sodium oxide? And I gave you the enthalpy of formation and the enthalpy of atomization in the problem statement. And we are able to look up the ionization energy and electron affinities in table 8. And we are going to sum those together, making sure that all of the arrows are pointing the right way in order to determine the delta H of this lattice. So when I say that the arrows have to point the right way, I'm saying that this arrow I flipped, and I flipped it because I am trying to get from the lattice to the gas phase ions. And to do that, I'm going to go around the circle the other way. And so I made sure that all of the arrows were pointing toward that target of the ions in the gas phase. Only one of the arrows had to be flipped. It was the formation. And so I summed all these values together and I got the lattice enthalpy. Don't worry, it's going to be your turn in a second. So there are 3 questions for us to ponder in the general field of Born-Haber cycle. So we're going to be looking at the Born-Haber cycle to make magnesium chloride. And I have some intermediates along the way. More common now than asking you to do the whole problem is asking you to do pieces of it. So I have never seen a question that says, hey, can you draw the entire Born-Haber cycle for this? Instead, it will be, what is this step in the Born-Haber cycle? Or what is the enthalpy change for this little section of it? So here are some examples that I tried to work up that gave you that sense of we're doing a couple of steps. One more time, it's really common in these questions to have some values given in the problem statement because they aren't in the data booklet. So even though you have to be an expert with your data booklet, you're still going to have to make sure that you check the problem statement for any values that you need. We're going to try to calculate the enthalpy change for magnesium solid becoming magnesium 2+ gas phase ion. And then we're going to try to calculate the enthalpy change for taking chlorine, the molecule, and turning it into chloride, the anion. And finally, we're going to try to put that together and use a Born-Haber cycle to figure out the enthalpy of formation of magnesium chloride. This is the hardest problem I have for this meeting. And if we make it through this, I think you should be really proud of yourselves. I know you're going to do great on your exams. I know they're coming fast and furious, and I wish you the best of luck. But let's put in a little work and see if we can use Born-Haber cycles to do this. So the first step, what I want to do is I want to take magnesium solid and turn it into gas phase ions. And so what I'm thinking we're going to need to do is we're going to need to atomize that magnesium. And then I'm thinking we're going to need to ionize that magnesium. And then I'm thinking we're going to need to ionize it again. So I've set up this cycle where the question was asking me to go directly from magnesium solid to the gas phase ions. I don't know how to do that, but I do know that the delta H that they're asking me for has to be equal to the sum of each of the steps. The delta H of atomization of magnesium plus the delta H, that is the ionization energy of magnesium. It's going to take me a second to find that in the book. 738 plus the delta H, that is the second ionization energy of magnesium, 1451. So the delta H is just going to be the sum of these three values, 2, 3, 3, 7. And so now, in a lot of ways, we have prepared the magnesium. So if you think about the Born-Haber cycle, this was in the element step where we have magnesium solid, the metal. And over here, we're in the gas phase ion step. So the elements are related to the enthalpy of formation. I think this problem is all going to come together. Let's see if we can do another piece and make some sense of this. So here we're going to take the chlorine. Again, I have the element. And I'm going to turn it into a gas phase ion. And to do this, I'm going to have to break apart the element, the diatomic molecule, into chlorine atoms. That's going to be the bond dissociation enthalpy of chlorine. And then I'm going to have to add an electron to the chlorine. And that's called the electron affinity of chlorine. And I'd find that value in section 8. So the overall delta H for this step is going to be equal to 1/2 of the bond dissociation enthalpy of chlorine. I think that number is 242. Plus the electron affinity of chlorine, which is -349. So here we are. The delta H for this step is equal to -228 kilojoules per mole. So you can see this relies on your understanding of adding reactions together. It relies on your knowledge of what's in the data booklet, so what's available for you to solve this problem. And it's just a little subset of the Born-Haber cycle. So these are pretty reasonable questions that can be worth a couple of marks, whereas a Born-Haber cycle, if you go way back in the syllabus, they had really giant questions that just aren't popular anymore. So as long as you're familiar with what the individual steps are, what the definitions of the different enthalpies are, I know you can do great on this. Overall, if we wanted to find the enthalpy of formation of magnesium chloride, that's going to be the enthalpy of taking magnesium solid and chlorine gas and combining them together to make magnesium chloride solid. What we've already figured out is that we could take magnesium and turn it into magnesium 2+ and 2 electrons. That was question A. And we've already figured out that we can take chlorine and turn it into Cl-. And that was the answer to B. So let's finish this up by recognizing that I need to do 2 chlorines and that this final step would be the delta H of the lattice written backwards. So I don't know this value. This is what I'm solving for. But the delta H that I'm solving for, the delta H of formation, is going to be equal to the answer from A plus 2 times the answer from B minus the delta H of the lattice, which I can find in the data booklet. The delta H of the lattice is 2540. The answer that we got in A was 2337. And the answer that we got in B was -228. So if I add those 3 terms together, being careful with my signs, the enthalpy of formation of magnesium chloride is -659 kilojoules per mole. Again, I think this is the hardest question in my review session tonight. It's taking the Born-Haber cycle and using it, but trying to solve a problem that's formatted a little bit differently. So seeing that steps A and B gave us a lot of insight into how to do it, and maybe showing us that we didn't have to redo everything. Now, if you like to think about what the Born-Haber or Born-Haber formula looks like, I told you that formation and lattice enthalpy are equal to atomization, ionization, bond dissociation, and electron affinity. And so if you go back and you look at step A, what we did was we calculated this term. We took the atomization of magnesium and the ionization of magnesium, both steps. And in part B, we calculated this term. We broke apart the chlorine molecule into chlorine atoms, and we gave electrons to the chlorine atoms. We did that for one chlorine, and we need to do it for two. In this problem, we're solving for the enthalpy of formation, and so we would just subtract L from both sides. And that is the formula that we used right here. So if you like to think about things in terms of a formula that you can remember, this might be another way to approach it. So you can think about it in terms of balanced chemical equations and adding them together. Or maybe you can just remember the general form for how Born-Haber looks. Never one to let me down. I was looking for a way to remember this formula, and so I typed it in, and that's a forensic llama. So you can see his police badge on him, his magnifying glass. That's formation and lattice enthalpy. And what is my forensic llama doing? He is actively investigating delinquent elephants. I love their peanut bags. They've stolen peanuts. Actively investigating, that stands for atomization of the metal, ionization of the metal, bond dissociation of the nonmetal, and electron affinity of the nonmetal. So again, if you're someone who really can take advantage of a silly picture to remember something, I hope this will help you. You can also write out the full Born-Haber cycle or think about it in terms of the balanced chemical equations, just for fun. If you haven't filled the form, feel free to fill it out. So Aisha said, in general, do we start with the metal and then the non-metal? I do typically do the metal first and the non-metal, just because I've solved the problems enough that I do a little bit better if I do them the same way every time. Kirtika has asked a few questions. The last one was about what a thermochemical equation is. That's just a balanced chemical equation with delta H written next to it. When we put the standard state symbol on something, that means that we have 1 mole of the compound, and we have 1 mole per decimeter cubed of a solution, and we're working at 298 Kelvin, and we're working at 100 kilopascals. That's what the symbol on top of enthalpy means. I don't understand the question that I just got in the chat. It says, does enthalpy change reaction direction? So if we want to change a reaction, if we want to run the reaction backwards, we will change the sign of the enthalpy. So if A goes to B has an enthalpy of plus 10, then B goes to A will have an enthalpy of minus 10. So I hope that's what that means. So here's another multiple choice question that I took from the RV website about the Born-Haber cycle. It's asking you to look at the different steps, X, Y, and Z, and just talk about what they are. So I think a huge part of this is just understanding the different steps that are going on. And so if you know the answer, feel free to throw it in the chat. Or if you have a guess about the answer, feel free to throw it in the chat. I'm going to take a little drink of coffee. And I won't lie that this is one I've hotly debated, but in step Y, I can see that potassium is becoming potassium plus. Whenever we lose an electron, that's called ionization. In step Z, I can see that chlorine is becoming chloride. Whenever we gain an electron, that's going to be related to the electron affinity. So it's atomization that's pretty tough. Atomization is going to be defined as taking something and converting it into 1 mole of gas phase atoms. And so the atomization of chlorine is going to be this reaction, where I make 1 mole of gas phase atoms. The atomization of chlorine monatomic would be this reaction, where I'm taking chlorine gas and I'm turning it into chlorine gas. So this delta H is equal to 0, and it's not what we did here. We used the molecule, we atomized it, and so I think the best answer here is atomization of chlorine. Of course, I am a big fan of using bond dissociation enthalpies. I can only use those for gas phase things. It would work great for chlorine. So in my examples, we were going to section 11 and using bond dissociation enthalpies. But if we replace that halogen, if this question was about KBr, we couldn't use bond dissociation enthalpies anymore because bromine is a liquid. So we do sometimes atomize instead of a bond break for the nonmetal, but most of the questions seem to use oxygen and chlorine. And so I think this one was tricky, but you guys did a fantastic job. Oh my goodness. The last enthalpy cycle I want to dazzle you with is about hydration and solution. So hydration is when we take 1 mole of ions and we dissolve them in water. So we might take something like chloride in the gas phase and dissolve it in water to make it chloride aqueous. These are all exothermic reactions. We get the great intermolecular, or there's no molecule here, we get the great inner particle force of the ion with the dipole of water. And so due to that good interaction, we're going to release energy when we let the chloride ions swim around in the water. The enthalpy of solution is about taking 1 mole of a solid ionic compound and dissolving it in water. And there's a big chunk of the data booklet that's dedicated to solving these problems. You have the lattice enthalpies that we already found in section 18. We have the enthalpies of hydration, which are in section 20, and we have the enthalpy of solution, which is in section 19. Again, this formula looks kind of crazy, but the problems, I hope, are really manageable. Someone's asking how this relates to the 2025 syllabus. These values aren't in the data booklet anymore, but I think being able to construct the cycles is fair game. So I think some of the definitions, like what is the enthalpy of solution, might be only appropriate for a 2024 student. But for a 2025 student, as long as the equations were given, I think the questions are absolutely fair game. We should be able to make an enthalpy cycle out of anything. So with that in mind, let's see how we could solve a problem about hydration and solution. I have a little bit of misgiving about this problem. Maybe it's too complicated, but I just wanted to point out that for the delta H solution, we can do it in the lab. And I wanted a quick problem on 5.1. This study session is 100% focused on the 2024 exams that are coming up this month. I just got a question about how 2025 was looking, so I answered it, but everything here is straight from your syllabus in the order of your syllabus using the tables in your data booklet. So I hope that I wasn't too confusing about that. Very much a 2024 oriented, I have exams this month kind of session. So in part A, we're going to go into the lab and we're going to try to measure the enthalpy of solution. And again, the enthalpy of solution is about taking 1 mole of an ionic compound and dissolving it to make ions. So we're going to calculate that using the techniques from 5.1. And then part B, we're going to try to use some of these new values. So we just got this experimentally. In part A, we're also going to take some values from the data booklet, and we're going to determine the delta H of hydration of our anion oxide. So we actually just did a problem where we calculated the lattice enthalpy of sodium oxide. We're going to do this experiment in part A to figure out the delta H of solution. We can look up in our data booklet the enthalpy of hydration of sodium in table 20. And so we're going to solve in part B for the enthalpy of hydration of the oxide ion, which I think isn't in table 20, though lots of things are. So I think it's fun. I think it's a good connection of things. But we haven't talked about calorimetry today. That's 5.1 in your syllabus. And it's going to be pretty quick, I hope. So 2 grams of sodium oxide is dissolved in 100 cubic centimeters of water, and the temperature goes up. So I know the reaction is exothermic because I can see the water's getting hotter. Where did that heat come from? It came from the chemical reaction that was taking place in the water. So can we use this to determine the enthalpy of solution of sodium oxide? And the answer is, of course, yes. Back in section 5.1, you might recall that the big formula was that the heat generated, or the heat, is equal to the mass of something times its heat capacity times its change in temperature. And so I think I could tell you how much heat was absorbed by the water because I know something very similar to the mass of the water. Since the density of water is 1, the volume in cubic centimeters is approximately equal to the mass in grams. So I know the mass of the water. The heat capacity for water is a known value. It's in the data booklet at the very beginning with some other constants. I'm going to throw down that value right here. It's 4.18 joules per gram degree Celsius. And the change in temperature is right here. So I could tell you how much heat was absorbed by the water because I know each of the 3 variables. But what's more important is that I know that the heat of the water came from the heat lost by that chemical reaction by dissolving the sodium oxide in water. And so I'm going to be able to figure out the delta H for my chemical reaction because it's going to be the amount of heat that was given off divided by the number of moles that reacted. So I think of this as a 3-step problem, and I'm just going to do the 3 steps with you. The heat that was absorbed by the water is going to be equal to 100 grams times 4.18 joules per gram degree Celsius times the change in temperature, which is going to be 41 minus 22.6. And so the heat that is absorbed by the water is going to be equal to not there. Sorry. I got 8832. And so the heat that was given off by the reaction is the opposite, the negative of that. And the difference between heat and enthalpy in our class is just the units. Delta H is going to be the heat divided by the number of moles. Oh, well, we have this number in grams, so let's quickly go over here and recall that the number of moles is equal to the mass divided by the molar mass. So the number of moles is going to be equal to 2 grams of sodium oxide divided by 2 times 22.99 plus 16.00 grams per mole. I think that's the right molar mass. It's going to be 4652.62. So it's going to be 2.00 divided by 62 moles. Let me throw that in my calculator. I'm getting 0.032 moles. So barring any rightos, I have minus 8832 divided by that number of moles. I get minus 273.792 joules per mole. All of the values we've been working through today are in kilojoules. So I'm going to call this minus 274 kilojoules per mole. Do you feel free to tell me if you don't agree with that answer? I was looking for an excuse to throw just a little bit of 5.1 in here. So this was a quick calorimetry problem. Calorimetry problems are always seemingly solved by this trio of equations. We're going to measure the temperature change of an object. We're going to know its mass and its heat capacity. That's going to allow us to determine how much heat it absorbed or released. We're then going to use the fact that the chemical reaction that took place was responsible for that change, and so had the opposite change. If you got heat, I lost it. And that delta H is then just the heat of the reaction divided by how many moles reacted. I often throw a limiting reactant here just to remind myself that it's actually the moles that reacted. So on we go. We're now going to see if we can use this value to figure out the delta H of hydration of oxygen in our most glorious and final super tough enthalpy cycle. So I'm going to look at this last problem and say, determine the enthalpy of hydration of the oxide ion based on part A. So in part A, we learned that the delta H of solution of sodium oxide is equal to minus 274 kilojoules per mole. The lattice enthalpy of sodium oxide we previous got tonight. And the enthalpy of hydration of sodium that's actually in the data booklet. It's minus 424. All right, let's see if we can do this. I think those are all of the values we need. So overall, what we're talking about doing is taking Na2O, the solid, and we can turn it into Na2O, Na plus gas, two of them, and O2 minus gas using the delta H of the lattice. So this value here is 2234. But we've learned a new trick. We could also take Na2O, the solid, and dissolve it in water to make two Na pluses, aqueous, and O minus 2, aqueous. All right, that seems reasonable. This is the delta H of solution that we just calculated in part A. We got minus 274. And then you can maybe see the delta H's of hydration. The delta H of hydration is going to be taking this gas phase sodium and turning it into aqueous sodium. So that would be 2 times the delta H of hydration of sodium, because there are 2 sodiums being hydrated. And the oxygen, we can also hydrate, and that's the value we're actually looking for. So if we use our new skills with cycles, we're interested in solving for that black line, for the hydration of oxide. And to do that, we're going to have to come up with a different path around here. One way is by looking at the formula at the bottom that reminds me that the lattice enthalpy plus the enthalpies of hydration of the anion and the cation are equal to the enthalpy of solution. So what I'm saying is if you add these steps together, you should get this step. We are trying to solve for the enthalpy of hydration of oxygen. And so we can write down that the delta H of hydration of the oxygen, or oxide, I should be saying, is going to be equal to the delta H of the solution. That's going to be minus 274. And then I'm going to have to subtract the enthalpy change of the lattice. We got 2234. And I'm going to have to subtract the enthalpy change for the hydration of sodium. That's going to be 2 times minus 424. So overall, we are predicting that the delta H of hydration of oxide is going to be minus 274 minus 2234 plus 848. I'm getting negative 1660. I have a cute cartoon to see if I did an okay job with that. This is my final answer, 1660 kilojoules per mole. But here's my sweet little cartoon. Ah, too much, too much. What I hope that you saw us doing was thinking about the lattice, thinking about the gas phase ions, and thinking about the aqueous ions. And one more time, we were trying to solve for this enthalpy change. And we did it by noticing the relationship that the delta H of solution was equal to the delta H of lattice plus the delta H's of hydration. Hydration do tend to be kind of large negative values. The smaller the atom and the more charged it is. So oxide having that 2 minus charge will make it a bigger number because it's going to have a stronger interaction with water. So always exothermic, and most exothermic for things with a really high charge density. I was also asked if the recording's going to be posted. Absolutely. The recording will be on the website. So that was our last enthalpy cycle for today, hydration and solution. It's kind of deep in the weeds, but it's a very similar problem, just with some new definitions. And so one thing I was hoping might help you see what's going on is just this little cartoon of where the different ions are. So again, we take them from the lattice to the gas phase to the solution. That's the cycle that we have in mind. And then one more time, I have a silly mnemonic to help you with this. But you know, it's a few pages away. This is my favorite one. Sloths, happy, hairy, and lazy. And so what that's supposed to convince you of is that the enthalpy of solution, S for sloth, is equal to the enthalpy of the hydration of the anion and hydration of the cation and the lattice. So you can obviously think about this in terms of the balanced chemical equations. You can think about this in terms of a cartoon of what the ions and atoms are doing. And you can think about this maybe in terms of just this simple mnemonic. I don't know why we use them all for electrochemistry and we never have any for anything else. So I'm trying to come up with some. Maybe that will make you smile on the exam. As a double check, if you want to see how you're doing with this idea, what I'm asking you to do is to solve for the enthalpy change of hydration of magnesium ions, and I gave you the other values. I'm going to give you a second. You can throw your answer in the chat. This is right on the verge of not having a calculator, but hopefully we'll be able to deduce if we're right or not without having to do any arithmetic. Okay. Thank you for throwing that in there. I said sloths are happy, hairy, and lazy. I'm interested in the enthalpy of hydration of magnesium. And so I'm going to tell you that it's equal to the enthalpy of solution. Then I've got to bring these things over to the left-hand side. So I'm going to use a minus. The enthalpy of hydration of chlorine, I'm going to need 2 of them because there are 2 chlorines in magnesium chloride. Minus the enthalpy of the lattice. And so now we're going to do our best estimating. I have a number really close to 2,500, and I'm going to add it to a number that's close to 150. So I have like minus 2,650. And then I'm going to add to that a number that's pretty close to 700. And so I'm going to get something that's around minus 1,950. So that's my rough math underneath. It's just trying to make some approximations. So I called 2493 2,500, for example. So I had a chance with the math, but I feel pretty good that the answer here is going to be negative 1920. And again, we have an ion that's really small, magnesium, and it's got a really big charge, 2 plus. So I think this is probably correct. B. If you have any more questions, I'll be here for a minute. I have one more question for you. Which row of the table correctly represents the equations for the enthalpy of solution of sodium chloride and the enthalpy of hydration of chloride? Very much, this is a definition-focused piece. And again, thank you for answering in the chat. The enthalpy of solution is taking sodium chloride and putting it into the aqueous phase. Sodium chloride is a solid, so choices C and D are incorrect. The enthalpy of hydration is about taking a gas phase ion, in this case chloride, and making it into an aqueous phase ion. And so A is the best answer, just as you said. The enthalpy of hydration is taking a gas phase ion and making it an aqueous ion. The second choice here, where we have the molecule chlorine becoming the aqueous phase ion, would take a whole lot of steps. So we would have to break that bond to make chlorine gas. And then we would have to add an electron to make chloride gas phase. And then we could hydrate it. So that B answer just has a whole lot of steps involved. And enthalpy of hydration is a single step, taking an ion and making it into the aqueous phase. So there you go. That was my last question. Again, A is the right answer. Thank you so much for coming. If you have any questions in the chat, I'm happy to be here for a little bit longer. These slides will be available on the Revision Village website, and I can try to get you that link again if you want it. But of course, there's just no pretty way to do this because it's going to be all the way at the start. Just be too nice if I had quick access. Ooh, feedback. Thanks for sticking with me. And if you have any questions, again, feel free to ask them. I hope you have really good exam session. I'm rooting for you. There you go. If you want to click on the notes. I appreciate you all. We'll keep doing these sessions before the different exams. So if you're a 2025 student examining in May, expect to hear about some of these in late April or early May. Absolutely. Right, I'll give you a couple of minutes to see if there are any other questions. Otherwise, I hope you have a great day or night. So if a reaction is exothermic, the temperature will go up, and if a reaction is endothermic, the temperature will go down. We talked a little bit about the formula you might use. We said something like Q is equal to MC delta T. So if you are putting out a lot of heat, the temperature will go up. And if you're taking in a lot of heat, the temperature, if a reaction is putting out a lot of heat, the solution that it's sitting in will get hot. If a reaction is taking in a lot of heat, the solution that it's sitting in will feel cold. If you have a more detailed question, I'm happy to answer it. All right, my chat's not blowing up, so I'm gonna stop this. Good luck with your exams. Have a wonderful day.